Hey there, it's time to talk about the dot product of two vectors. So this is now we're going to start getting into how vectors relate to each other when you try and do operations with them. And it's going to build upon what we've already talked about, like the unit vector and magnitude. So those are all basic components for being able to talk about what we're about to talk about right now. So dot product is not necessarily when you want to multiply two vectors. Let's take two vectors and put them right here. So let's say we have vector A and vector b. And we want to do the dot product. Now we cannot use the multiplication sign. We have to use a dot because it's not necessarily multiplication. Because we're taking two components. What I mean by component is the coordinate thing with the angle brackets, and we're doing a type of multiplication, but it's not actually multiplication like what we're used to with like 9 times 6 is 54 and other stuff. We're getting an entirely different result that has an entirely different meaning because we're no longer talking about just numbers, it's vectors. So dot product does involve multiplication in when you're trying to do it. And I'm going to start with explaining how to solve for it, and then I'm going to explain kind of what it means, dot product, and what it relates to. So to solve it, fairly simple. Let's say A is equal to, I don't know, like 513. That's x5, y13, or a change in each of those. B is, let's go random number like 8, 5. Right. So how do you calculate the dot product? Nothing more than the x values. So I'll write the equation right here. X1 times, and you can use multiplication symbol right here, times x2, like this is, plus y1 times y2. Simple. So this one would be x1 times x2 would be 40 plus y1 times y2. 13 times 5, I don't have that one right in my brain immediately, so we'll have to calculate. 13 times 5, 65. Who knew? So 40 plus 65, this one I can do in my head, is equal to 105, if you can see that. So, strictly speaking, that's how to calculate the dot product. Easy enough, right? Now, what does the dot product actually mean? Like, what is it referencing? So, this is where it gets more confusing, and it took me a bit to figure it out. But we're gonna go along with it. So the dot product is how much two products help each other or influence one another when, well, when two vectors, how much two vectors influence each other when they're going in different directions. So this is when we have to start talking about the angle between two dot products. I mean, two vectors, not dot products. Um, so let's say we have vector A here, vector B here. Let's not forget that the location is arbitrary. We're just sticking them together. And we'll have angle theta here. Where really there's the angle is going to be important, and I'm going to explain why different angles or key angles like 90 degrees, 180 degrees influence. But let's go back to the definition. Dot product is how much two vectors help each other. So, or influence each other, you could say. These vectors are kind of going in the same direction. So they're not going in opposite directions, nor are they going in a perpendicular direction, but they're actually influencing each other. And even if A was going off in this direction, the opposite one, that would still be an influence. So the dot product is asking how much do they influence each other? To what extent? So the way you calculate it is you're essentially taking the magnitude of one and the magnitude of the other. No, that's not right. It's yes, that is. It's the magnitude of one and the magnitude of the other times the cosine of the angle. So the formula for this is actually magnitude of A times the magnitude of B times the cosine of theta. Now this is exactly equal to A dot B. Like, this is exactly the same thing because it's talking about how much they influence each other. So I have to think about what does cosine mean in this instance. So if we look at these two together, um, well, let's think back to our trigonometry with SOHCAHTOA. SOHCAHTOA. So this middle part, the ka, is the cosine is equal, cosine theta technically, is equal to the adjacent over the hypotenuse. And so what we're doing is we're taking the adjacent and the hypotenuse, which are these two. The adjacent is this one's the hypotenuse, and multiplying them by the cosine. So in my mind, I'm pretty sure that this essentially equates to A dot B is essentially B squared, but I'm not 100% on that. I think that I actually have to verify that, but I'm fairly sure I'm making it. But basically, the cosine is a scale, and then we multiply it to tell how much they're going against each other. But here's an observation. Let's say that A and B are at a 90-degree angle. This is our first example. This is where it really started coming together for me when I started thinking about them in terms of what happens when they're at certain angles. So let's say that these are two forces acting on a box. So vector one, this will be B, this will be A. Like, let's say they're acting on a box. This one's moving in this direction at 0 degrees. This one's moving at a direction at 90 degrees. And of course, this right here is 90. So the question is, how much do these two vectors influence each other? Does one pull one away from its trajectory or not? The answer is no. So if you want, I mean, that's not the best way to explain it, but this vector going up does not influence this vector going to the side. That's about the best I can do. So what this comes out to over here is magnitude of A. Let's say it's 8. Let's say magnitude of B is 6. That's not actually what it is. Times the cosine of theta, which is actually 0, is equal to A dot product B. I'm going to erase this up too. So it's equal to A dot B, which is equal to 0 because they're multiplying by 0 right here. So why is it 0? It's because if A is 8 and B is 6, this is essentially taking the components 0, 8, and dot 6, comma 0. You take the dot product like we calculated earlier, which is 0 times 6 plus 8 times 0, and you get 0. Multiply that by cosine, which is, wait, hold on. I messed up. It's not the components. We already have the magnitudes. Though those are the magnitudes. When you do it, you're supposed to take the magnitudes. Wait, no, I was right. No. So the components come out to be like 8, 0, 6, 0. Like, this comes out to be 0. And then when you take the magnitudes, which are 8 and 6, which are 48, and multiply that by the cosine, which is 0, I'm just going to scrub out the cosine by 0, you still get 0. Because, I'm going to say theoretically, because I can't actually prove why, these two vectors don't influence each other. And the cosine is essentially saying how much they influence each other on the, ooh, that's interesting. So the cosine is saying how much they influence each other on the unit vector scale, and then you multiply in these by the magnitudes, determining how how far, I think how far, like the magnitude of how much it screws up. That makes a bit more sense. So I hope you realize that the first part of the video is actually official, and the second part of this video is me theorizing and learning, which is the point of this. But hoping that makes more sense. The cosine is zero because these don't actually mess with each other. And so no matter what your magnitude is, you don't have a dot product because they don't mess with each other. Now, if you make this like 89 degrees, you do get a dot product because it's no longer they actually mess with each other. Like this one is slightly leaning to the right. Is they do now influence each other, so therefore you have a dot product. And and yeah, that's dot products. Next, we're going to talk more about this formula right here, which can be used to calculate a bunch of different things. But since I've already gone off the rail, I doubt you're still watching, and I can't exactly make a chapter. So we're going to stop it right here. Some theories about and observations. We're going to call it observations on dot products. And, and yeah, we're going to stop it there.